So good evening, everyone. First of all, I would like to thank the organizer for inviting me to give this talk. It's also an LHCb talk on the latest result on open and high and heavy flare production measured in heavy ion collisions from LHCb. So although Julia just presented the detector, I will myself also have a few slides about the LHCb detector. Then I will go through some of, I've selected latest and selected results, mostly in P-lead collisions, because this is where we have, we just saw lead-lead results, but we also have very nice P-lead result to complete the physics program. And since we were ending the questions on the detector upgrade and future performance, I have a few slides also to highlight a bit what we would expect from the new detector. So let me start with the usual LHCb detector. So you just saw a few things in the previous presentation, and especially this sketch where you see that LHCb is a single arm spectrometer, which is fully instrumented at forward rapidity. On the sketch, on the, let's say the graphic on the right, the picture on the right, you also see how the different subsystem of LHCb compete or complete with the other LHC experiments. And basically, well, since LHCb initially has been designed to measure B mesons in PP collision, it has some interesting features that are fully relevant for heavy flavor measurement in P-lead and lead-P collision as well. So first of all, there is a track reconstruction down to PT equals 0. We also have an excellent PT and mass resolution, a very performant and fully performant and particle identification system to identify all the particles, but also a precise vertex reconstruction to really disentangle B mesons from prompt from non-prompt production. So there is also another thing unique in LHCb is the possibility to not only run in collider mode, which is PP, P-lead, and lead-lead collisions, but also we have the possibility to use a fixed target setting where actually we inject gas inside the vertex locator tank here. And you have on the right simulations on the vertices we see when we inject this gas, only noble gas at the moment, so helium, neon, and argon, to get this very nice fixed target program ongoing. A bit of an illustration of the LHCb performances before we go to the results. What I mean by mass resolution, good particle identification and vertex reconstruction are illustrated here on this slide. So on the left, you have the invariant mass here of B mesons in the D plus K channel decay from PP collision, and we can clearly see how good we perform to disentangle all these kind of contributions in the B sector, but that works as well for other particles. In terms of particle identification, you have here an idea on the performance on fixed target proton-helium collision, where you have on the x-axis this, let's say, particle identification quantity, and you can clearly separate here, for instance, pion, proton, and kaon plus fake tracks with this quantity. And finally, in terms of vertex reconstruction, you have a small illustration here where you see clearly the distinction between the vertex of the collision and the vertex of the decay for this B sub S event. We'll see later one slide about the status in lead-lead collision. So on this slide, you have a list of some of the LHCb results that have been published in heavy ion collision. On the right here, you can click on this link to have all the details and to have this basically all the public results available. On this presentation, I will focus mainly on 4 of them, starting with the latest one in the open, in the charmonium sector, which is the Chi-C production. You are probably already familiar with the Chi-C as it is a charmonium, a CC bar state, which means that, it shares, this particle shares basically the same physics motivations as the other CC bar states. So in P-lead, you would You would be sensitive to nuclear PDFs, or let's say cold nuclear matter effect in lead, which is not measured at the present, I think at DLHC, but at least in HCB, you would be able to have a probe for your QGP studies. In addition, the feed down from KC represent roughly 30% of the prompt production. It means also that you need to understand how what's going on with the KC if you want to have a full description of your gypside production in PP collisions or in other colliding system. Experimentally, I would like to say that actually the KC is quite challenging to measure, because if you look at the decay channel here that we use to perform this measurement, there is a photon in it, and the photon is usually very difficult to measure from the experimental point of view. But in HCB, we measured actually the KC with two different mode of photons. You can on the left you have the invariant mass spectrum. So this is the KC mass minus the invariant mass of the gypsy. Here, this delta M variable using a converted photon, where you see the KC, clear KC1 and KC2 peaks with a very nice resolution in P-lead collision, but with very low statistics. On the other hand, we can do the same measurement with calorimetric photon or direct photon, but here, although we have much more statistics for the KC, we have a lower resolution due to the calorimeter actually. But nevertheless, we measured for the first time the KC in heavy ion data at DLHC. You have on the right the ratios of the cross sections in lead P here at backward rapidity and in P-lead at forward rapidity using converted and calorimetric photon. And these results have been compared here on the same plot with the PP reference at 70V that we measured. So basically, since we are limited by the statistics, I mean, we see that our ratio actually is compatible with unity both in P-lead and lead P, but also compatible with what we see from PP collision at 70V. And well, we'll see later on when we have a bigger data set how we can improve this measurement. So the next type of results that I would like to discuss are baryon to meson ratios here in P-lead collision, because these studies have been done in HCB in the B sector and in the charm sector. So let's start with the beauty mesons and baryons, beauty mesons and baryons measured in P-lead at 8 TV. So on the left side, you see on the top plots are actually the ratios of the cross section of, in red, B0 over B plus, and in blue, lambda B over B0. In P-lead on the left, lead P on the right, versus the transverse momentum. And on the bottom, you have now the nuclear modification factor ratios. So compared to the two, you have now a scale to PP collisions for the lambda B over B0 versus PT here and versus rapidity on the right. And basically what we see is, well, a flat dependence of the B0 over B plus ratio versus PT. But a baryon to meson ratio that is dependent on the transverse momentum for the lambda B over the B0, which is also seen here in the RP-lead of the ratios of the RP-lead of the two cross section, with also maybe a hint of a relative suppression in lead P compared to PP collision, which we don't see in at forward rapidity, but this is to be confirmed with more data since we are still at less than 5 sigma or from unity. But extensive studies you will find in the paper show also good agreement between data and Laconia prediction with several sets of NPDF for this measurement. So this brings me to the same studies, but in the charm sector with the charm baryon to meson ratio, measured at 8 TV, which are illustrated here on the plots. So on the top row, you have the lambda C over D0 ratio of the cross section versus PT in P-lead on the left and lead P on the right. And you have the same plot here on the bottom, but with a slightly different rapidity ranges range, sorry, just to compare to see how the PT dependence evolve if we reduce a little bit the rapidity range in the center of mass system. Basically, what we observe is a flat, or let's say not strong dependence of the relative lambda C to D0 ratio versus PT and rapidity, but still with a decreasing trend versus PT in PLED, as you can observe here on the left row. There is usually, when we compare to theory predictions, which are the curves here on the plot, so EPS 09 prediction or NC Tech here, there is a general good description of the nuclear modification factors, both at forward and backward rapidity, but also when we look at the ratio. All these extensive studies are in the paper, if you're interested. Well, this is still within large uncertainties of the model in some cases, especially if you look at single RP-led or at production cross sections. There are also, if you look here, some kind of tension still at higher PT in PLED collision when you look at the ratios of the cross section on this sector, actually at forward rapidity. Is it due to data fluctuation or, let's say, additional effect that is not taken into account in the theory predictions? This we will have. We will need more studies to really have a strong statement on this. Well, we also are now performing open charm production, measuring open charm production in the PLED collision in the new sample. So yes, indeed, I forgot to mention. So these, so this is a typo actually. So these data are at 5 TeV, but now we have a new, well, we have recorded in 2016 an 8 TeV data sample with much more statistics, and analyses are ongoing for the open charm production in PLED collision. On these plots on the left, you have preliminary results for the D0 cross section versus transverse momentum. And you can see that we have, well, a lot of statistics in forward and backward rapidity. And on the right, we have performed this forward to backward ratio, so PLED over LED-P cross-section ratio versus the transverse momentum. In black, you have the old data sample at 5 TeV. In red, you have the new data sample at 8 TeV. And basically, between the two, we have improved the statistics by a factor of 20 compared to by a factor of 20 due to the luminosity. And if you compare to, let's say, here, this NPDF predictions for the ratio, we start here to see a clear tension at high PT between the data and the theory predictions, which means that we might need an additional effect to really fully understand this theory, these data. So the analysis is ongoing, not only on the D0, but also on the other open charm states with the lambda C as well. And we hope to have them out very soon or published very, very soon. So just one slide on the status of the nucleus-nucleus collision. As Julia, well, Julia just presented basically two of the first two measurements we perform in the lead-lead sample. And she was mentioning the fact that we have trouble to reconstruct event or to record event in most central collision. A way to illustrate that is to look at this kind of plot where you have here the number of velo clusters, so the number of clusters in the velo tracking station, so near the interaction point, and versus the calorimeter, which is a detector that do not saturate here. And basically you see a very typical saturation pattern, which means that there is a loss of tracking efficiency, obviously, but also because, well, the velo is fully on, is saturating. That means that we are still limited to 60% centrality with the current data we have, but it means also that we can still do very nice physics with these data. So not only the result that Julia presented, but there are ongoing analysis on the D0 lambda C to D0 ratio ongoing. So you have here these preliminary plots with basically the statistics we have collected between 60 and 90% centrality. So enough lambda C's and D0 to really start to have a nice analysis for this. For these particles. But also we have recorded at the same time a fixed target sample, this lead neon sample at 69 GeV. And the good thing with this sample is that there are no saturation effects as in lead-lead. So it means that we can reconstruct the full centrality range in lead neon. And you have here preliminary plots with the number of gypsi we've recorded. So both these analyses are actually ongoing and hopefully would be ready very, very soon. So stay tuned for further informations. Okay, so now let's, go to the last section of this talk, which is a bit of an outlook on the detector upgrade and the future performances. So here on this slide, you have, basically LHCb detector for the season 3, so 2022. So the design and the upgrade was thought was based actually on the PP collision requirements we will have with the new run 3 data, which means a collision rate of about 40 megahertz. And a pileup factor of around 5, so 5 PP collision per bench crossing, which is for us a good news for lead-lead collisions, because it means that the average multiplicity we will record, or we are trying to aim at for PP collisions is higher. So we will expect better performance in lead-lead, as Julia just presented in the previous talk. But basically, what we will have is a new pixel velo detector, which will not saturate as the previous pixel detector. Also, new tracking stations upstream and downstream the magnet, with the UT here, and also a scintillating tracking fiber detector called the Sci-Fi. The Reach will have new optics and new photodetectors, and basically the only detectors or subsystems that will remain roughly unchanged are the muons and the colorimeter system, because we just here changed the electronic. And the idea with this new detector is to have a full software trigger, which means we will remove any selection based on the L0 trigger, so on the L0 trigger level, and we will reconstruct data in real time on the flight, and yeah, so full software trigger and reconstruction with the new LHCb, which means a full readout of the detector at 40 megahertz. You have for projections this study, which is a little bit outdated in terms of the scenario for the luminosity, but in this document you will see, with the reference here, you will see studies for the D0 bar correlations, B plus meson production and Drellian production for the run 3 with what we would expect from the new LHCb detector. I won't go through the three studies. I will just illustrate actually show the B plus meson production with these two plots. So these are the nuclear modification factor of the B plus versus the transverse momentum in P-lead and lead-P collision. So in this scenario, basically for the systematics, we assume that the performances are roughly similar to what we had in run 2, except for the tracking, where we assume that it is a little bit improved. And for the statistics, we assume here 4 weeks of data taking for a total number of 500 inverse nanobarn. The data point you see here are actually based on theory predictions from Elaconia plus EPPS 16 and PDF predictions, so nothing based on data. So this is pure theory driven, except of course the uncertainties. And the message here is that with actually a limited number of data taking period with the new detector, we would be able in the B sector, but that works for other probes, to really have valuable inputs for NPDF studies and for heavy flavor measurements with LHCb in P-lead collision. That works as well if we get something else like a proton oxygen run. Maybe someone will discuss that later on during the workshop. But in any case, we will have a very, very performant detector for heavy flavor in P-lead collision for sure. Another thing that will change is the fixed target program of LHCb. Because previously we were injecting gas near the interaction point. Now we will have this very nice cell, which is called SMOG2. You have a link of the TDR here, which is the standalone gas storage cell cover that will be installed actually just before the vertex locator detector. You have here a picture of the SMOG system, which is this tiny thing here. The velo is there, and actually you can already see that it is installed and ready to be commissioned, ready to go. The advantage of this new SMOG cell is that we will have a factor 100 on the gas density with the same gas flow of the previous SMOG, but also we will be more accurate in terms of the density. Well, actually the measurement of the density inside the system. In short, it means more statistics, but also a better control of the luminosity, the uncertainty of the luminosity for with SMOG2. And last but not least, since it is outside of the velo tank, there might be a possibility to run in parallel of PP collision for the full data taking year, the full year, but also to inject non-noble gas such as hydrogens, but this is still to be fully confirmed. Nevertheless, on the top left, you have projection of the luminosity and the yield, or say the number of particles we would be able to reconstruct, assuming a full year of data taking in parallel mode of the PP program. And this brings me to my summary. So I hope you are now convinced as me that LHCb is a very performant heavy flavor detector at forward rapidity with a large catalog of precise measurement in PP, but also an increasing number of results in P-lead and fixed target collisions. There are, as I said, many analyses ongoing, which should be ready soon. So the D-meson studies in a P-lead collision at 8 TeV, the lambda CD0 ratio in peripheral lead-lead collision, but also the gypsine D0 measurement in this lead-neon fixed target collisions. And for the future, well, we will have the next run 3 will help us to improve the quality of the data with the installation of this this new detector with an improved performance in terms of tracking and PID efficiency, but tracking and PID efficiency, but also with the evolution of the fixed target program with this new SMOG2 device, which means better performance expected for run 3 in high multiplicity collisions, both in P-lead, SMOG, but also in lead-lead collision. And with extended capabilities, it means also we will have an expansion of our physics program. And I would like to thank you for your attention.
Thank you very much for this overview of the LHCb heavy ion collisions. Is there or ask the questions on the chat? No? Ask the questions here from the audience? Go ahead. No, you change your name.
Okay, Benjamin, thanks for this nice review.
Hello, Paul.
2 questions. Since from my memory, Chi-C2 is a state that can be formed by just the fusion of 2 gluons, so it should be relatively simple to predict. Basically, are you able, from this nice measurement that you did, and in P-lead somehow to constrain better the models on the quarkonia production than just by looking at gypsy or psi prime? Or what are the additional constraints on constraining the model, you know, between this color singlet and blah, blah, blah?
Yes. You mean directly from the Chi-C or in general?
From the Chi-C, which is easier basically to model, as far as I remember, as resulting from this 2 gluon fusion.
Okay. Well, I mean, It would be easier in PP collision, right? The data set at 7 TV is already published and has much more statistics. So I think they have. I'm not sure exactly what if they fully have studied the decay in terms, for instance, of polarization or other stuff. But in principle, I would say we can do that. And I think that there is also something. I'm not sure if the paper is out already, but there is the PP13 TV result that should be around. So in the PP sector, we will have enough data to perform any analysis possible. I don't know them in detail though, so we have to check the paper.
The Shaman allows me a second question. Thank you, Shaman. Then, have you seen any kind of anomalous physics in your PLED analysis where some kind of QGP droplet would be mandatory to explain any of your results, or does the full?
I mean, there is an open question, at least. Well, I mean, at least from my point of view, I'm not sure if this is due to a QGP droplet, but one of the anomaly that we see in PLED, I mean, the one that I'm interested in at the moment is this lambda CD0 ratio, because if you compare to Alice, there is here a clear difference for this lambda C to D0 ratio at mid rapidity or at forward rapidity between Alice and HCB. So this is something we already know, but this is still something we would like to check. There are analyses that are ongoing, a bit more like in the Alice style, where we look at multiplicity dependent results. So there were this chi-C not so long ago, but now we are working on, for instance, B sub S and other results versus multiplicity in PLED to actually see, to check or to study, as Alice did, this kind of multiplicity dependent effect, and if we can have something different from what they see due to the fact that we are at forward rapidity.
Thank you.
Okay, can you just start, right?
So it was again on the KC. So I was wondering, it looks like in principle you may have all the ingredients to have directly the DRP for the KC2 and KC1 separately.
The what? Sorry, I missed part of the question.
Yes, no, I was wondering about this KC result. You might in principle have all the ingredients for calculating the RP-LED separately of the KC1 and KC2, or am I missing some ingredients?
So for the PP reference data, we will need a PP extrapolation, but let's say this at the moment, I mean, should be possible to have and to work with it. The only thing is, at the moment we did a ratio because it is much more, it's easier to well, in terms of systematics and in terms of measurement, because the photon is very to have the absolute efficiency of the photon, it is a bit tricky. So in principle, we have all the ingredients. The question is that we need more time because it is not very easy to have a let's say the efficiency for the photon, especially, I would say.
So, well, just one thing, we don't have the chi-C1, chi-C2 absolute procession. We only have the ratio as well.
Okay, yeah, this information I didn't have. Thanks.
Yes.
So, combining the two.
Well, okay, the chi-C to your side is a 7 TV, is a very small statistic. No, that we also have it. Yeah, but I mean, we could do the modification part for the ratios. Chi-C1, chi-C2 in PLED, chi-C1, chi-C2. I don't know if that's interesting. But absolutely, we don't have it. Okay.
All right, let's please go because we're running over time.
About the lambda C over D0 ratio, I was wondering also about the trend that you observed in the charm and in the beauty sector, whether you can interpret the different PP trend in the sense that for lambda B over B, you see a trend in PLED, and also in PP, it's LCB showed a spectacular measurement of the PP dependence of this ratio, which decreases with PT.
Mm-hmm.
wondering whether you expect them to be different between charm and beauty, and whether this is expected in the Laconia prediction. Here you say that Laconia describes the data, while here you say that the type it doesn't, and the prediction is rising with PT.
Yeah, so the description is let's say correct. So sorry, let me start with this lambda B over, let's say, baryon to Bayesian in the B sector versus charm sector. So I think they will be expert this week, but as far as I understand, the difference you would expect, since you have a B, you would have maybe a similar structure when you look at, because when you do this kind of ratio, you would probe at first order the hadronization mechanism. So either fragmentation, coalescence, competition, or completion for this kind of measurement. So I would expect that for the B sector, since the mean PT of the B would be, I don't know, maybe slightly higher, and this is probably what we see, we would expect the similar, not that slide, a similar trend, but with this kind of typical peak, or let's say, not sure, small increase, maybe at higher PT compared to the charm, if you believe that there is such a thing as a kind of a bumpy trend. What I was saying with the NPDF set is that for the nuclear modification factor and the forward-backward ratio, it works within the large uncertainties, assuming that these points are, let's say, it's still less than 5 sigma away. So we can't exclude formally a fluctuation from the data. Let's say if you look at these this other result in a range which is smaller, you see that actually the difference that we see here is less, is not as big as what we observed there. So let's say we can't conclude strongly on this, I would say, due to the uncertainty.
Okay, there are 2 questions from outside, but please answer shortly, because otherwise.
Sure, I will try my best.
Yeah, can you hear me?
Yes.
Okay, yeah, it's a follow-up essentially on the same point on these predictions. I was wondering, do you know in these predictions with different initial state effect, how the fragmentation is modeled? Because you see a difference between lambda C and D0, which makes this ratio not to be flat and to be placed around 0.3, but this should come from how it's modeled the hadronization. So do you know how it is treated in the package that you used?
I don't really know the full the details. I know this is a Laconia, so I would assume plus different NPDFs. So I would assume that you only have fragmentation, but I'm not. I don't really know in detail the answer.
Okay, last one is from Min. Min, you hear us?
Hello. I also want to ask about this lambda C to D2 ratio. See here, the rapidity dependence is pretty weak. But I remember there was a tension between the measurements by Alice as a mid rapidity of this ratio, and the LTCB measurements at fold rapidity, right? So it's these measurements still in conflict with the Alice results or not?
Yes. Let's say Alice here, if I would have to put Alice data, if I recall correctly, it's like you have this bumpy shape, but it is higher. It is at 0.6 or a bit higher compared to what we. So it's still there. Yes.
Okay. Thanks.
Thank you very much. Let's talk. Thank you, Stig, and at the time.
Thank you.